Welcome back to another calculus video. Today we're going to be reviewing some basic information about functions and specifically inverse functions, and just some ways to describe functions that are important in the vocabulary, might pop up somewhere down the line. It's also just good math to be exposed to the kind of thinking and the kind of terminology that you might see later on in higher mathematics. So let's talk a little bit about what it means to be a function. We define a relationship. So we always start with a relation, right? A relation it can be an equation, it can be a table, it can be a graph, but basically you're taking two different variables and you're talking about the relationship between the two of them. That's called a relation. We say that the relation is a function if when you take the input values, we call that the domain, when you take the domain elements, so whatever you can put into this relation, and then you look at what you get out of the relation. If when you put a number in or a value into the relation and you only get one element of the output, we call that the range, back, we say that that relation is a special relation. We say it's a function. And graphically, when we look at a graph of a relation, we look at it in terms of, maybe you are familiar with something called the vertical line test. And what that shows us is if we take a vertical line and slide along our graph anywhere, and if the vertical line only hits the graph one time in every place, it'll never hit it twice in any spots, then that's a visual representation of that concept, because by hitting it only once, we're saying at that value of x, there's only one corresponding y value. So for every input, there's exactly one output. Now, we're going to talk about yet another classification of functions, and that's called a one-to-one function. So what this means is that we have a function where not only are we going to plug something in and only get one answer back, that's what makes it a function, but we're going to say that that answer that we get back is unique. There's no other x that will give me that y value. So if I plug 2 in and I get 5, there's nowhere else where I could say plug in 4 and also get 5. For every x that I plug in, I'm only going to get one unique y value back. So that's what it means to be one-to-one. There's no other two values that you're going to see linked up in that way. So every element of the domain is paired with one unique element in the range and vice versa. So how do we tell if a function is one-to-one? Well, here's a couple of examples that we're going to start out by exploring, and we're going to think about these analytically. So if it's one-to-one, if I plug in an x, so for example, if I plug in the number 1 in question A, I'm only going to get the answer 4 back. There's no way, and if I think about the graph, there's no way, this is a linear function here, there's no way that I can get, multiple values back when I plug in an x number. So like for example, I can plug in 5 and I'm only going to get 8. There's no other x value that will give me an answer of 8. So this function, and as a matter of fact, all linear functions are one-to-one. We say one-to-one, that's going to be my little notation. Now, but then when we look at question B is a parabola. It's y equals x squared. So, for example, if I plug in the number 3, when x is 3, y is going to be 9. The problem is there's also another x value that gives me 9, and that's negative 3. So because there's two x values that give me that same output, this, even though it's a function, it's not a one-to-one function. And whenever we are asked, is it one-to-one, we're often asked to justify our answers. This is called a counterexample. So if I'm trying to prove that it's not one-to-one, I can just find one example. That's all I need is one example where it doesn't meet the conditions. And this is called a counterexample. And it's a great way in mathematics to prove something is not true. So using this counterexample. Graphically, it would look like this. You'd have a parabola here, and you would see that, boom, if this is 3 and 9, on the other side, you'd have negative 3, 9. So there is your graphical representation. That's what it would look like. And I want you to kind of keep an eye on that too, because, we talked a lot about this whole vertical line test. But is there some visual representation that we can be thinking of that would tell us if a function is one-to-one? So be thinking about that. The last example here is the absolute value. And similar to question B or equation B here, this has that absolute value graph. It's a V-shaped graph, and it's very similar to the parabola with regard to this question. And, you know, if you, let's say, plug in 4, you get 4 back, right? But it also works when you have -4. So while this is a function, it is not a one-to-one function. So I'm going to say no. Now, when we think about one-to-one functions, the reason why we're concerned with whether something is one-to-one is because when we look at a function, oftentimes we also want to consider what's called the inverse function. And we've discussed this in previous videos. But the inverse function is essentially the function where the domain and the range are exchanged. And the inverse is not always going to be a function. Sometimes it is and sometimes it isn't. Sometimes it'll just be an equation or a relation. Now remember, to be a function, when I look at the equation that I have, when I put one number in, I only get one number back. And in an inverse function, compared to the original, the domain and the range have been exchanged. They've been flip-flopped. So now what we're going to do is we're going to explore this concept of being one-to-one, and we're going to look at some graphs, and we're going to look at some inverse functions. So we're going to stick with these 3 examples, and we're going to take a look at what Desmos has to say about some examples that we have going on here. Desmos is a fabulous free resource for graphing. I highly recommend checking it out. It's super easy and intuitive to use. So as we look here at what we've got going on in Desmos, get it nice and easy on the screen here. So remember, if I have a function, so here's our first example, and I am going to graph its inverse. Now remember, the definition of an inverse is the domain and the range have been exchanged. So literally, all I have done is flip-flop the x and the y here. And you can do the same in Desmos. So here's this, and here's the inverse function. And you can see that if I were to test the dotted line, that's the graph of the inverse, with that vertical line test, it is a function. So here in example 1, we were one-to-one, and the inverse is a function. So now let's take a look at example 2. Y equals x squared. Now we said that y equals x squared, yes, it is a function, but we discovered that it was not one-to-one. Let's take a look at the inverse. Here it is. Now, the inverse function is this dotted line, and if I try to pass that vertical line test through just that dotted line, you're going to see that it's failing. It's not going to, like at 5, if I pass a vertical line through the inverse graph, the dotted graph, it hits it twice. So here, my original function, y equals x squared, was not one-to-one, and the inverse was not a function. Curious. Maybe you see where I'm going. Last but not least, here's our absolute value function. It is a function. It was not one-to-one. Here is the dotted inverse function, or inverse equation, and it is not a function. It fails that vertical line test. So what I want you to do is I want you to think about, okay, where am I going with this? Number 1, what's the relationship between an inverse being a function, yes or no, and being one-to-one, and the original being one-to-one? And then the second question is there a visual, like we have with the vertical line test? Is there a visual that we can use to determine if we're one-to-one and if our inverse equation will be a function? And hopefully you have come to the same relationship or visual that I have, and that is this. When you consider the visual, a good visual tool for the original function, anytime you're determining is something a function, is our vertical line test. But if we take our original function and we pass it through a horizontal line test, that's going to tell us if our function's one-to-one. If the function's one-to-one, then when we go to find the inverse will also be a function. So let's write that down. A function has an inverse function if and only if the original function is one-to-one. We're going to add to this information about passing that horizontal line test. So we're going to use the vertical line test. That tells if the original equation is a function. The horizontal line test tells if the function is one-to-one. If it's one-to-one, then when you go to find the inverse, it will also be a function. So let's consider this. Why do we care about being one-to-one? Well, this equation y equals sine of x, you've seen this in pre-calc. We know that sine is a function. It is not a one-to-one function. And we know this because in pre-calculus, when we go to solve equations involving sine and solving for angles, we can get lots and lots of angles. Every time we go around the unit circle, and we land at pi over 2, it's just a multiple of pi over 2, and it has the same sign. So we can also see that it's going to fail that horizontal line test if I make a sketch of the graph. Now, why do we care about one-to-one functions? Here's just a little bit of relation. Let's relate this back to pre-calc or trigonometry or whatever course you took prior to calculus where you learned about the unit circle. You also should have learned about something called a principal value. And the principal value allows us to be able to have y equals capital S sine of x. It also allows us to do the principal value, the inverse. Okay, so it allows us to have one result back. So when we do that inverse sine, that's also a function, and we only get one answer back, and it's always between negative pi over 2 and pi over 2 for sine. So this is how we relate this whole one-to-one concept back to trigonometry, back to inverse sines, and all the things you did when you were solving for equations. But let's go ahead and see a few examples here before we leave off. Example 1 says, find the inverse of this equation and state whether the inverse is a function or not. So first off, this is the equation of a line. A line is always a function, and we learned earlier that a line will always be one-to-one. So this is one-to-one. The graph is a line. So yes, the inverse, and here's your notation for the inverse function, f to the negative 1 is a function. Now, let's find the inverse function. Step 1, I'm going to write it with a y. Step 1 is to exchange the domain and the range. So we flip the x and the y, and then we just need to solve for y. So we're going to subtract 1 and divide by that negative 2. You can also write it by dividing through on the negative. Negative x plus 1 over 2 would be an equivalent form. And yes, this equation is a function. So now let's do example 2. Find the inverse of f of x equals x squared. And notice it tells me some information here. It says x is less than or equal to 0. So let's talk about how we would start by finding the inverse of this function. We're going to set aside that domain restriction of x being less than or equal to 0. We're going to pretend like it's not there just for the beginning, because I want to talk through a couple of key points that are important for later on in this course. So if y equals x squared, then x equals y squared. Now we have to solve for y, and here's where it gets a little tricky. We've always been taught that when we solve for y using a square root, we always need to include a plus or minus sign. So we end up with something like this. Y equals plus or minus the square root of x. Now, here's the tricky part. Why do we use the square root? So here's a little side note, and this is important for later on in calculus, so make sure that you're paying attention. Just because it's a side note doesn't mean you don't need to know it. We've always been taught that when we solve for x squared, we get a plus or minus, right? So when you have, when you're solving for a variable, that's just the way that we do it. Now, here's why. When you solve using a square root, you have to understand that whatever number is underneath, so for example, if I plug in 5, I'm going to get the square root of 25, which is 5. So it works out. But the trouble is, when I solve for negative 5, I'm going to get the same result. I'm going to get 25 underneath. So it's very curious what's happening here. And when we respect that proper order of operations, doing our, square roots and our squares in the right order here, we end up with this problem. And so what you need to understand is that when we solve the square root of x squared, truly what's happening is you're getting the absolute value of x. Now, we also learned in the piecewise functions lesson that the absolute value of x can be expressed as a piecewise function. So we let it be x for all the positive values and 0. We let it be the opposite of x for all the negative values of 0. Or sorry, for all the negative numbers, anything less than 0. So here's the tricky part. When you're dealing with this problem and understanding what's happening here, truthfully what's happening, if I go back over here, is we've got this whole middle step here that we got to figure out. And it ends up being like this. The absolute value of y is equal to x. And so because those y values could be positive or negative, because we have this piecewise function over here, and yes, it uses the letter x's. Don't let it be confusing in that way. Whatever you're taking the absolute value of, you have to consider both the positive and the negative values of it. So over here, we have to do the same thing with y. We have to consider that, oh, y could be positive or y could be negative. So we have this struggle and this fight here when we're trying to solve when we take the square root of something squared. So here is why when we drop absolute value bars, and I left out my radical. When we drop the absolute value bars, we have to throw in the plus or the minus. And that's because of that piecewise function. So really what we're saying is y could be positive square root of x or negative square root of x. That's the piecewise function that we did over there. Now, it's positive square root of x for certain values, and it's going to be negative square root of x for other values. Now, here's where that domain restriction comes back in. So we're going to go back up here, and we're going to remember that when we find the inverse function, we're actually exchanging the domain and the range. So for the inverse, if my original function says x has to be less than or equal to 0, for the inverse function, that's going to become the restriction on the range. So we only want answers that are going to be less than or equal to 0 here. So what that means is we want that set of values. We want the negative square root of x because we want our y values to come back at us being negative. So here's where that domain restriction comes into play. So because of this, and because of all the thinking that I've had to go through, the inverse is actually y equals negative square root of x. Now, is this a function? The answer is yes, and here's why. When we go back up here to the original function and we graph it, we have a parabola, right? Y equals x squared. But we only have the x values that are less than 0. We only have this half of the parabola. So it actually passes the horizontal line test. And if we were to graph this square root function, it would be the bottom half of a sideways parabola. So here's where our mathematical thinking takes us on this crazy journey, and we have to pay attention to all the little details. And this is something that, as we get into higher mathematics, this type of thinking is what you want to spend your time doing, just thinking logically through it. Why do I have this domain restriction? What does this do to my problem and my functions? And as always, we always want to remember that when we verify that two functions are inverses, we walked through this in the composition of functions lesson. When we verify, what we do is we say, when we do the composition, we get x. So we can also think of it like this, using that inverse notation. That's kind of weird. So that's how we can verify that two functions are inverses. And as always, as you guys are walking through this last one was kind of a doozy with the level of thinking that we kind of did through it. But I just want to encourage you that, you can do this stuff. You can think your way through it. You can wrap your brain around it. I can't tell you how many times I have sat and thought through deep mathematical concepts, and I think I get it, and then a moment later I'm like, wait a second, did I actually get that? And there are still concepts today where I am blown away and my mind is just boggled as I think about some of these things. And the more you think about them, the more you dive in, the more you apply them and practice them, the better you're going to be. So you can do this, and just keep at it, and I'm here for you. You've got this.